Welcome back, guys. This is part 5 of the final project for the Stellar Robotics 2018 CAD class. We left off last time having finished the gearboxes and getting all the wheels and drive motion components in the assembly. This time what we're going to work on is we're going to get the belly pan in here, and we're going to start working on some lightning. I'm probably going to break the lightning up into 2 separate videos. Just to make the videos a little shorter, because otherwise it's probably going to be pretty long. So what we're going to do for the belly pan is basically it's gonna start as a rectangle that goes almost to, that sits on top of this flange, is flush with the inside of these plates, or rather this part here, not the notch, and then runs all the way across and to the other side. Then we're going to do some notching. We've got a notch out. We've got to add this notch in so that it's actually flush with this part as well as this part. There's no reason that the belly pan needs to come all the way to this inside bend here in this front and the back channel. However, it does need to come all the way to the front for the part that's under the inside drive rails, just because we need the drive rails to be fully supported with all 3 of these holes. If that doesn't make sense, once we get this kind of in here, you'll see the shape that I have in mind. We're going to start with a rectangle though, just because that will make this quite a bit easier to model. We're not going to try to get the exact, and then we'll just add cuts and things to do the notching. Then in addition to that, we're also going to have to add a cutout for this gear, because it'll stick through the bottom, as you can see in that view there. Alright, so let's obviously we can't bring it all the way to this face because we've got the bend radius in here to contend with. The bend radius is about 1 millimeter, and that just has to do with the radius of the punch and the opening of the V-die. I think we're just going to take off a 1/16, so we'll just set the front of the belly pan a 1/16 off of this inside face, and the same on the other end. So if we just measure from the inside of the end drive channel to the other channel, we get 31.375. And we're going to take a 1/16 inch off of each end, so that'll be an 1/8 inch overall. So this is 0.375 is 3/8. So if we take an 1/8 off of that, it's 2/8, which is a quarter. So it'll be 31.25 long. And then let's measure, not the notch part, we're going to measure from here to the other side, 16.5. Alright, so let's create a new sheet metal part for this. Actually, no, we don't need a sheet metal part. It's not going to have any flanges or anything. So sometimes you add some flanges to your belly pan to mount stuff, but in this particular case, we're not going to do that. Alright, so it was 16.5 wide and 31.25 long. This is going to be the front, and then the back will be at the bottom, but that doesn't really matter for this particular drivetrain just because it's going to be symmetrical front and back. But in a lot of cases there will be differences. Alright, let's finish that and extrude it out. It's going to be a 1/16 of an inch thick. You can go thinner than that if you need to, but when you're supporting heavy components like the battery or even the power distribution panel on really thin metal, you have to add some stiffening flanges and stuff. We're not going to model like a battery box or any mounting for electronics. Typically you would create special holes in the belly pan and then lighten around those holes so that you have specified mounting locations for your electronics, but that's kind of outside the scope of this project, so we're not going to bother doing that. Alright, so this is our starting shape. So what we need to do now is set the material to aluminum 5052 H38. So now what we have to do is we have to add the notches in the front and the back, and then we have to add the notches on the sides. We're going to start with the notches in the front and back. So basically, I don't want the belly pan to be on top of these 2 rows of holes right here. we really only need to catch this front row of holes. So we can kind of just cut that material out. And the reason you cut that material out is just to save weight. You can cut a, 1.5 or an inch wide strip of metal, 16 or 15.5, no, 13.5 inches wide, roughly. And you can just get rid of that piece of metal. So that's the reason we should do that. So what we're going to do here is we're going to create a sketch, and then we're just going to model both sides. So I need to project as construction geometry this whole front face. I'm just going to click on the face, and it projects all the edges that make up the border of that face. And then I'm going to do a 2-point rectangle, turn off construction geometry, place one corner on the construction line and the other corner just down somewhere. Then I'm going to do this down at the bottom. I did not let it automatically line these up just because I'm going to go up here and I'm going to place a collinear constraint between these two sides of the rectangles. So now these two sides of the rectangles are lined up with each other. So now what we can do is we can dimension the distance between these edges to be 1 inch, which is just the width, that's just the part that's under the drive rail. And then the other side will be the same. Alright, so now we don't have to do that down here because we use those collinear constraints. Now we should dimension the depth of the cut. We're going to make this so it's going to be basically we want an inch overlapping this. Well, we would normally. However, in this particular case, an inch is a little bit overkill. We don't really need a full ½ inch on the inside of these holes. We can go with 1/4. So actually, close that. So if we measure from here to here, we want basically, we know these holes are inset 1/2 inch, and we just want to go another 1/4 inch on the inside of that. So that's 3/4. We basically want 3/4 of an inch of metal overlapping this plate. So we need to subtract that 3/4 of an inch off of this number, and then we need to get rid of that 1/16 of an inch gap we've got. So there's already, this is a 1/16 shy of 2 inches, because we're taking the 1/16 off for the material thickness here. So if we take off another 1/16, oops, so 1.9375, we subtract another 1/16. You could do this in the sketch, but I don't see a reason to do that in this particular case. And then we're going to take off our 3/4 of an inch. That gives us 1 1/8 inches. So get out of that. So then this dimension needs to be 1.125. And then down here we're going to place a dimension as well, and then just click on the first dimension and then click the green check mark. Alright, so now we can extrude this, and we'll just go distance, extents all, and click OK. It automatically switches to cut mode when we do that. Alright, let's give this a save real quick, and we'll just give it the next number in the series, which will be 10. Alright, so now we have to add these notches here. So these notches are, I'm going to measure from here to see the other one here. So that notch is going to be 27.5 inches long, and it's 1/8 of an inch deep. I remember that from before, and it's going to be centered. Excuse me. And it's going to be centered in the side of into the side of the belly pan. So let's create a sketch, and once again I'm going to project geometry, but I'm only going to project these two sides. Alright, so I'm just going to place these rectangles down here in the middle, and then I'm going to use a coincident constraint up here to constrain the center of this side of the rectangle to the center of the projected line. And then the same thing on the other side. So now I can dimension the width of this, or the depth of this cut, to be 1/8 of an inch. Do the same thing on the other side. I'm just going to click the first dimension and then press enter. Then I can dimension the length of this to be 27.5, and I can do the same thing on the other side. Click on the first dimension and press enter. Alright, so now I can finish the sketch, extrude, click both regions, extents all, switches to cut automatically like it usually does. Alright, so now we've got these notches. Alright, so now let's add some mounting holes. So we know we're going to need a row of mounting holes across here, and we know we're going to need one down each side to match up with these, and the ones down the side to match up with these. So dimensioning this is going to be tricky. Well, yeah, so this edge here is a 1/16 inch away from this face, which is the inside face of the drive rail, or the end channel, sorry. And that is a 1/16 inch away from the outside of the drivetrain, and we know that these two hole patterns, this hole pattern and this hole pattern, start a 1/2 inch on center from the absolute outside of the drivetrain. So we've got a 1/16 inch for the thickness of the material, and then another 1/16 of an inch until this plate starts. So we know this is an 1/8 inch away from the outside of the drivetrain. We know the holes are on center, 1/2 inch from the outside of the drivetrain, so we can subtract that 1/8 inch, meaning that these holes are 3/8 in from this edge. So let's just throw some holes in here and pattern them all the way down the side, and that should give us the result we want. I'm going to just use a construction line here, press enter to get rid of that, switch to the point tool, place a point at each end point of the line. Then I can dimension from the line to there. We just said this was 3/8, and this will be a 1/2 inch in from this, because this is what representing the width of the drive rail, and the holes are inset a 1/2 inch. So now I'm just going to press the H key to do the hole tool. You don't even have to finish the sketch. We're going to switch this to a simple hole. We're going to change the size to be 0.196 for the rivets. Click OK. Then we're going to select our rectangular pattern tool up here on the ribbon. Click on the holes. It selects both of them because they were created in the same hole feature. Then we got to pick a direction. Just pick an edge. That's the correct direction. If it's not the correct direction, you can flip it using these arrows as usual. The hole spacing is going to be a 1/2 inch, and I believe there were 62 holes. Click OK to that dialog, and yes. Alright, so now there is actually a hole here, but we're not going to be able to rivet to it, so we're going to start our hole pattern here. This edge here is 14.5. So basically, the first hole is going to be a 1/2 inch in, because everything's a 1/2 inch spacing, so we can kind of just make some assumptions based on where the holes are located. So let's create another sketch here, and we know there's going to be a hole here and a hole here, and we're going to pattern in this way. So I'm going to do kind of what I did before, except turn 90 degrees, where I create a line. And all the line does is it just stops me from having to create a vertical constraint, so that I have kind of a visual reminder that these two holes are lined up vertically. I could use a vertical constraint, but this is just kind of an easier way to remember. And I realize I forgot. I'm going to finish this sketch real quick. I'm going to go back to my hole 1 feature, and I completely forgot to dimension this on this side. That should be also a 1/2 inch, just like it is over here. Alright, so I'm going to finish the sketch. I just got it close enough that I didn't notice that I had forgotten. Okay, so let's go back and edit the sketch we just created. Alright, so this is going to be, we know this is a 1/4 of an inch off of that edge, and the hole is going to be a 1/2 inch from that edge, and then this is also a 1/4 inch from this edge. Alright, so let's finish the sketch. Actually, I didn't need to do that. I always do that. Okay. Holes are 196. Then we're going to go ahead and rectangular pattern. Pick a direction. We're going to want a line running horizontally this time. That's the wrong direction, so let's flip it. 1/2 inch hole center. Was it 29? 28. Okay. So we're good there. Okay. All right, so let's give that a save. Let's put this in our assembly. Then we're gonna have to add some fillets and stuff just around the corners. We gotta figure out where we want these cuts to be. Actually, let's do this now. So we're gonna start the cut. We don't really need to put the cut underneath the shaft, but we're gonna go ahead and do it. So basically, we're gonna make the cut the depth, like the width of that. So 1.25, and then we just gotta figure out how wide we want it to be. I'm kind of thinking we want to go from like the center of this standoff to the center of this standoff because the gear is pretty close to the standoff. So let's measure the center distance of those two. And we know it's centered in the length of the drivetrain. So 3.498, we're just going to make it 3.5. Okay, so 1.25 and 3.5 centered. And then we know it's going to start on the inside of the drive rail, which will be an inch away from this surface here. So let's go back to this. Create our sketch. So we're going to have, we'll do these center point rectangles, create 2 of them, use a horizontal constraint to the center point for both. Should have dimensioned these. So this will be 1.25 and 3.5. Same for these 2. Alright, so now let's dimension from here to the inside will be just 1. Same thing on the other side. Remember, you've got to select this edge here. You can't select this edge here because it's 1 inch away from the outside of the drive rail, and this is a notched portion. So I'm just going to press the E key to go to the extrude tool. Once again, you don't have to actually finish the sketch to do these. I'm going to click the 2 regions, select extents all. It'll switch to cut. And we have our 2 holes, so that'll give us clearance for the gear. So let's put this in the assembly now. Place components. We're going to rotate it once by the y-axis, and if we rotate it by the x-axis, it's actually upside down. Now, obviously, this is symmetrical, but I modeled it expecting the top to be the front of the drivetrain, which is the end facing away from us. So I actually am going to flip it 2 more times. Place that down. All right, so we know we're going to go to the constraint tool. We're going to constrain the top of this to the bottom of the drive rail. I could constrain the bottom of the belly pan to the top of the inside of the end channel. It would be the same difference, but this feels more intuitive to me, so that's what I'm going to do. All right, so now, let's flush this edge here to this edge here. So flush. You could also do the notch, but this edge here is a more stable surface because if we ever came back and edited this drivetrain and changed the depth of the notch, it's better to dimension from here because we're more sure that the distance in between the drive rails is not going to change than we are that the depth of the notch is not going to change. Okay, so now we've got to dimension it in this direction. So I guess what we'll do is we'll just dimension that face, the farthest front face, to be 0.0625 off the inside of the end channel. Click apply. Alrighty, so let's holes are lined up, that's good. The notch is lined up, that's good. The gear is not hitting, looks good. There is a gap. Well, that's weird. Why is it doing that? That's a weird effect. That's a weird effect. Okay. There is a gap between the bottom of the bottom of the gearbox plate and the belly pan as designed. All right. Yes. All right. Yes, I wanted to analyze for interferences. So let's we can click on the drive, the belly pan. We can go to inspect. We can click analyze interference, and I believe there's a way. Can I window select? Yeah, you can just window select everything. So I'm just checking for interferences between the part that I selected and anything else in the assembly, and it didn't find any, which is good. I didn't figure there would be, but I just wanted to make sure. All right, let's go back and add just fillets on all the corners. I wanted to know what the radius of these were. 0.05, I think. Yeah. All right, so we'll just do 1/4 inch fillets for everything except these, except the notch. Oops. To deselect, if you click a wrong edge, just hold the control key and then click on that edge again, and it'll take it away from the selection. Even if parts don't have flanges, you can still create them using sheet metal. You just have to use a face tool. You just have the face tool instead of the extrude, and it's pretty much the same thing. It does make doing things like rounding corners easier because the corner round tool in the sheet metal environment won't select like these top edges up here. It'll only select actual proper corners, which is pretty useful. I've never been able to really get myself into the habit of using sheet metal even for parts that were flat, but that's probably a habit I should get into. Alright, and I'm going to round the inside of these. I'm going to make these 1/8 inch because I don't want the radiuses to interfere with the gears at all. And these pockets aren't really taking away a whole lot of strength out of this. The belly pan, we'll talk about that when I get back to the drivetrain here. Okay, so this is done, at least in this project. I'll explain a little bit more about that in a second. So let's go ahead and color this and make it blue. Just make sure everything looks good. Yeah, it's a little bit weird because it's a different radius, but that doesn't hurt anything. Alright, I guess I could have done 1/4 inch here. I'm actually going to do that because I would prefer larger radiuses. So you can just, to change a radius, you know, this is why we didn't do all of the 8, this is why we didn't do all of them in one go. So you can just go back to fillet 3. And you can actually add more lines here. I prefer to do it in multiple features, but you can also do it in multiple lines in the same feature. I don't really know what the advantages and disadvantages to doing it that way are. I'm always used to just creating separate features, and then I can kind of just go down the list and it'll highlight which ones are which, and it just makes them easier to find. Alright, so made those 1/4 inch. Go back to here, get an update. Yeah, that looks good. Okay, so normally, alright, so first of all, the belly pan is actually a structural component. So if you were driving around the field with your drivetrain and you got hit on the corner, your drivetrain's going to want to rack, right? It's going to want to basically pivot, basically rotate the drive rails around their mounts on these edges. And because this is only 2 inches wide, right, this doesn't give you a lot of leverage to support your drivetrain flexing in that direction. It is pretty strong, but it's in a high-speed impact, it won't be enough to keep your drivetrain from folding up on you. I mean, it'll take the impact, but you might shear rivets if it's a really bad impact, and you probably will end up tweaking something out of shape. Also, if you're driving over uneven terrain or while you're turning, your drivetrain is able to flex quite a bit, and it increases turning drag and just doesn't allow your robot to be very stable. So you want your drivetrain to be extremely, extremely rigid if you can get it that way. So adding a belly pan basically creates what is effectively one huge giant gusset, so that if you get hit, essentially all of the compression and tension and everything that wants to be focused on these end connections on the drive rails basically gets spread out across the whole belly pan, and it really, really helps to make your drivetrain stiffer. especially if you're putting a lot of rivets down the rows. It just kind of fuses your drivetrain into one piece much more effectively than it would be without the belly pan. The belly pan doesn't have to be metal on drivetrains. Obviously, most teams are using plastic or wood. Actually, we didn't really have a belly pan in 2017. We kind of just had multiple small pieces that mounted because that drivetrain was a lot smaller. There wasn't a lot of open space like there is in this design, and it had a notch in the front, which also took out a lot of real estate. So we kind of stacked our electronics vertically, and there were a few like smaller cross straps that we used to mount like motor controllers, and then we ended up integrating the battery box into one of the end channels, which was kind of interesting, kind of a pain, but it worked. That robot went through a lot of changes over the course of the season too, and a lot of them affected the drivetrain. So the drivetrain at the beginning of the season was different from the drivetrain at the end of the season by quite a bit. In addition to that, you'd be, like I said, mounting electronics to this. You would mount your electronics to this typically because there's a lot of open space here. Typically, your mechanisms can't make good use of this space, so you might as well put your electronics here. It protects them. It saves space up on the top of your robot. It also does a good job if your battery and your heavier components like your power distribution panel, which weighs almost 2 pounds if I remember correctly. If you're putting that all the way down, half an inch from the floor, it helps your center of gravity quite a bit. So the belly pan would almost never be solid like this. If we click on the belly pan, then right click and go to iProperties, go to physical, update it, you can see the belly pan is, the better part of 3 pounds. The belly pan, if you basically put a whole bunch of holes in where each, mount each electrical thing where you want it to go and put special holes in for it and then lighten around all of those, you could take out, at least half of that weight. A general rule of mine is just if you're lightening fairly aggressively, you can take about half of the weight of your aluminum parts out. There are exceptions to that, and probably as a general rule, it's probably actually a little less than half. But if you're lightening very aggressively, you could get half out. You're not going to really get any more than that because you're still going to have a lot of structural components or structural elements of the parts that you have to leave alone. You can't take weight out of. But if you're being aggressive, that's what you can do. So this belly pan could drop to 1.5 pounds, and 1.6 pounds maybe. And belly pans, that half is kind of an average over your whole robot. So certain things like the drive rails, we're probably only going to get a quarter of the weight out of these. But the belly pan, you might be able to get this down to 1 pound if you take a lot out. If you're adding a battery to this, you don't want to have the weight of the battery on the belly pan because the belly pan doesn't have any stiffening components, and it can sag in the middle if you get that 14-pound battery sitting on it. So typically our battery box sits on top of the belly pan, but the battery box has some stiffening elements that run across and connect between the two drive rails. Sometimes it'll be on top of the drive rail. Sometimes it'll mount to the side. Typically we mount to the side, but it just depends on what the superstructure of the robot looks like and whether the battery needs to lay down or it can stand up. Ideally, it stands up. That makes it easier to get in and out of, and it saves space on the belly pan, but typically having the battery sticking up, 3 inches above this gets in the way, so we typically lay it down, even though we'd rather stand it up. Plus, laying it down helps with center of gravity, too. Okay, so that's the belly pan. We're not gonna actually lighten it because typically you'd have electrical components on here anyway, so we're not gonna bother doing that. We are going to, for this video, we're going to lighten this gearbox plate, and then we're gonna color. We need to work on the coloring for the standoffs. I still haven't investigated exactly what's going on with the colors, so we may just have to recreate that color for every part that's yellow. The blue is a default Inventor color, but the yellow is custom. But really the gearbox plates and the standoffs are the only other parts that I'm going to make yellow, so we'll just cross that bridge when we come to it. Alright, so let's open the gearbox, let's open the plate. Alright, so what we're going to do is we're going to put some just kind of like curved slots in here. You want this outer, you could hack this outer circle off, like just it doesn't have to be like this. And I personally, I think you can get away with it without any negative effects. However, most of the people that I've heard talk about this typically say you want to support the whole face, and it just provides a little extra support to keep the motor from kind of like flexing this way or that way. And it's such a critical component. You know, it's your drive gearboxes that you can't really afford these failing, and you really don't want these gears to strip out. So having the motors having a really like a full face, really rigid mount, it's good. That being said, you kind of want this outer rim for support, but you don't need this material in here because it's not really doing anything. So as long as you don't get too aggressive with it, you can take most of this weight out and still have the outer rim there to support the motor. So we're going to create a sketch. I think we're actually going to do some mirroring just to speed this up. I don't really like to do a lot of mirroring, but in this is probably a pretty good part to do it on. So we're going to just do one quadrant, and then we're going to mirror it down, and then we'll mirror both of those across to the other side. All right, so I'm going to turn on construction geometry. I'm going to project this outer circle. I'm going to project the motor circle, or the motor boss circle, and then I'm going to project this top hole. Okay, so next I'm going to create an arc. Yeah, it's got to be the center point arc, not the 3-point arc. Start on the center point here. We're going to create an arc there, and then I'm going to start on that center point again and create an arc there. Then we're going to connect these with lines. Then, because we kind of want these lines to radiate out from this center point. Actually, do we want that? We want this one too. We're not going to do it with this one. So we're going to create the coincident constraint tool, and we're going to attach this point to this line. Now the point's not actually on the line, but it's on, you know, where that line goes if that line extended to infinity in both directions. Alright, so next what we're going to do is we're going to create a construction circle that is 3/8 of an inch in diameter, which kind of represents the length of the standoff. We're just going to want this to be tangent to that because we just want to make sure that there's enough meat here that this can support that hole. Okay, so next we're going to create a horizontal constraint on this line because we just kind of want a ray coming out here just to connect this outer ring and the inner ring somewhere in the middle other than just here and here. You'll see once we mirror this. Alright, so now let's dimension from here to the center point. We're going to make that we want this ray to be, I think, 1/4 inch wide, so it'll be 1/8 of an inch because it's half, and that'll be when we mirror down. This will be 1/4 inch wide. I'm gonna make this 0.25 is probably too much. We'll do 3/16. We'll do undo with Control Z, D for the dimension tool. We'll do that's 3/16 there as well. We'll see what that looks like. When we're lightening this, we're just kind of going with what feels right. You could do stress analysis and stuff on this, but a lot of times you don't really know the details of about how much load is going to be on different components, and so you couldn't really do stress analysis unless you knew that stuff. So just kind of fudging it and getting close by looking at dimensions and saying, that looks strong enough. That's kind of the best you can do. So we're going to go to the extrude tool. We're going to set extents all. And then we're going to add some fillets in here. So we're going to fillet. We'll look and see what 1/8 of an inch looks like. What is 1/4 inch? Probably 1/4 inch is probably too much. Yeah. We'll stick with 1/8 of an inch. You got to be careful how close this hole gets to the edge, but like I said, we were supporting the full face of the standoff, so it shouldn't make a difference. Alright, let's mirror this to the bottom, and then we'll mirror it across. Now we're going to need our origin planes. We know we started with this hole in the middle, so we can use this origin plane to reflect left and right. We don't have one. This is our origin plane for the in this direction, and it's not in the middle, obviously, so we can't use it to reflect up and down, so we're actually going to have to create one. So we're going to create, basically we want it to be centered on these two holes. We want a plane that kind of bisects that. So we need to use, where is it? Oh yeah, 2 coplanar edges. This is what we're going to use, but we need the edges. We can't actually select the center line of a circular feature unless there's already an axis there. So we have to create a work axis there. We have to create a work axis there. Then we can click on plane, click on one axis, then the other, and you can see it creates a plane there for us. There's other ways we could have defined that plane. There's at least one other, probably more than that, but that's just a good way to do it. All right, so now we can click on mirror. We can click on the extrude feature, and then we also want to mirror the fillet. So we'll click on both of those features. We'll click on mirror plane, select our mirror plane. You can see it shows a kind of a preview of what we're going to do. We click OK. There we go. Okay, so now let's do another mirror, and let's find that plane there. Oh no, no! Escape out of that. Did that wrong. Okay, we gotta pick our features first. So we're going to. You can just pick the first mirror that we did, which is this one down here, and it should mirror both of them. So then we can pick our mirror plane. It's this first one, yeah, and it shows you a preview of what it's going to do. So we'll click OK. Alrighty. So now let's expand these axes that we created are inside of this work plane. So if you expand the work plane, there's your 2 axes. We want to. I'm going to hold Control and pick all 3 of these, and we want to just right-click and turn off the visibility because we don't need them. Okay, so now what we're going to do is we're going to create kind of a crazy lightning pattern in here, kind of following along the same thing. You kind of want all of your holes. You want to preserve the outside shape of your part for rigidity in most cases. You also kind of want to connect holes with some kind of like webs like this. You kind of want to have some like straight lines that are connecting most of your holes. You typically are going to want like some webbing in the middle, and then you kind of just want to take out your weight at angles, just so that you've got some pieces of material that are connecting all the important features. That way you're not losing strength. Okay, so let's create a sketch, and then a lot of this is visual. I mean, a lot of this is what looks good, because this is kind of teams do this lightning style for looks as well as for taking weight out. There are other ways you could take out weight, but they don't maybe look as nice. But this is an effective way to take out a lot of weight, preserve a lot of strength, and make it look really nice. So this is a good way to do it. All right, once again, we're going to just do 1/2 of this, and then we'll mirror it to the other side. But because the top and the bottom are not the same, because this hole is not centered, we're going to have to do the whole side as a whole. So let's project geometry and turn on construction lines. Let's project the holes that are important to us. We want the top and bottom line, and we're probably going to want this line and that line. This takes practice. You have to get really finicky with your constraints to get this to work. You're going to have to delete constraints and add a lot of constraints in manually. I'll try to go through that. That being said, when you guys are doing this, it's probably going to be different than when I do it, just because the way you place the lines in here are going to change which constraints Inventor infers automatically. So you've just got to remember that you can turn constraints on with F8 and turn them back off with F9 so that you can see which constraints are there and delete the ones that you don't want. So this might be kind of difficult for you guys to do, but we're going to do a lot of it during the season, so I suggest you practice it. Let's change some settings here. I have some settings changed in my Inventor. I just want to show you what they are. If we go to Sketch and we go to Constraint Settings and click on the Settings button, then we go to Inference. I have parallel and perpendicular constraints turned off. I have horizontal and vertical turned on. And then intersect, midpoint, on, curve, tangent, coincident. I have all those checked. So I turned off parallel and perpendicular. That's going to be important because these are going to want to infer automatically by default, and it typically makes this process a lot more difficult. So if you want your settings to be the same as what I have, turn those off, and then just click OK. All right, so now we're definitely going to want to connect this hole and this hole with the web. So we're going to want 2 lines in here like that. I'm pressing enter. I don't have to press escape. I can just press enter and the line tool stays active, but my line's not connected. So line and then enter. All right, I'm definitely going to want a web going vertically like that. I'm definitely going to want, I'm not connecting these 2 lines yet because I'm not sure that they are actually going to be connected. We're going to have something in here like that connecting these 2. Same thing down here. Press enter. And I'm trying to avoid, you see all these like dotted lines. I don't know how well they'll show up in the video, but these dotted lines that are showing up, this is showing that you're kind of aligning on points. When I'm placing lines in here, I'm trying to find a place where there aren't any dotted lines just showing up. That means Inventor is going to infer less coincident constraints, and you'll have to deal with stuff being lined up automatically. If you get a lot of these going, it's going to make your job a lot harder. So try to find places where there aren't dotted lines. You can turn those off, but in a lot of cases they help, so I don't turn them off. Okay, so we could just connect these 2 corners. We could put a little arc here or another straight line just to keep, because remember we want a 3/8 of an inch circle. Actually, let's turn on construction geometry and create a 3/8 circle here, and let's do the same down at the bottom. That way we can use this as a visual reference to make sure that we're actually preserving all of our geometry for our standoffs to sit on. So we could do this, or we could attach kind of a cross member in here. We could attach a kind of a web in here, although this web would get so close that there wouldn't be much of a hole here, so I really don't see a reason to do that. I don't really think we need a web across here. If you're being conservative, I would say put one there, but we're kind of being aggressive in this project with our lightning, so we're going to go ahead and leave this just open. And then, well, there will be fillets in the corners, which will help absorb the load. Okay, so now I want to know how far apart this and that are. That's minimum distance, 1/4 of an inch. Okay, so basically what we're going to do is we're going to create another line that's just going to go like that, and it's horizontal. And this will just connect directly to the arc for this circle, and then we'll round that off with a fillet later. All right, so I got to figure out how to handle this kind of corner right here, whether I want to create an arc in here or if I just want to create that tangent like so. And I didn't mean to make that vertical, but I guess it's fine. No, it's not. Okay, delete that. Okay. I don't want this to be vertical, but it keeps putting one there. I think we want it to go like this. Okay, so we want this line to be tangent to that circle. We want this line to be tangent to that circle. Then we're going to angle this back, and we're actually going to do the same thing we did with this, where we click on the line and click on the center point with a dimension and make it like 0.125. So that'll angle it in a little bit, but it'll ensure that we've got a nice web here for the strength, because you know, the weight of the motors and the load the gearbox transfers to the wheels is going to kind of get transferred through these standoffs. We want to make sure these are nice and sturdy. Let's do the same thing for this one. Oops, dimension to the line to the center point. And then let's click on the original dimension just because they're always going to be the same. Then I'm going to press escape to get out of the dimension tool and kind of move these dimensions. You're going to have a lot of dimensions. You're going to have a lot of dimensions that are tied to each other because you want them to be the same. All right, so let's create a coincident constraint. Let's join this to that, and let's join that to that, because those are just going to be sharp corners that will fill it later. We want these two lines to be parallel, so let's place a parallel constraint. This line is already horizontal. We want this and that to be attached, so let's join those two. All right, so then we need an arc here, we need an arc here, we need an arc here, and an arc here. So let's go back, create a center point arc, and let's connect to the center of this and the end point of that line, and we'll drop it there, and we'll place a coincident constraint manually. Then connect to there, and we'll place a coincident constraint manually. You can try to connect the end points of these lines while you're creating the arc, but I found it's typically, I get the best results if I place the constraints manually. All right, so let's do the middle here, like so, and we're going to connect there. Oops, it inferred a constraint. Okay, so it conferred an equals constraint between these two. You want to watch that because it's going to try to infer all kind of constraints that you don't really want. That being said, in this case, I was going to place an equals constraint manually between those anyways, so I'm going to leave it. All right, so next I'm going to pick a coincident constraint and hook up these 4 corners that did not connect before. All right, so now I want an equals constraint between this one and this one. I already have one here, obviously. Basically, we just want these to kind of look like a circle. We want this to look like a circle. We don't want different radiuses here and here. So we're going to actually project this arc here and just place an equals constraint just to make this line up with this. And that's just a visual thing. It'll look nice that way. All right, so I'm going to turn on construction geometry, project that arc. Then I'm going to set an equals constraint between those 2 arcs. All right, and then this one changes because these 2 are equal with each other. All right, so let's dimension from here to here, and we'll make it the same as what this is, which is 3/16, so 1875. And we're going to do the same thing on the bottom, and we're just going to set these 2 dimensions equal to each other and click OK. Then from here to here, we want this to be fairly strong. We want this to be probably 3/8 wide, so we're going to do it half of 3/8, which is also 3/16. And then we're going to do the same thing here, and because we want this to split the difference between the 2 hole centers, we'll set them equal to each other. Oh, right. Okay, so now we need a construction line, so construction geometry on. We're going to connect these 2 holes with a line, and then we want to set this parallel to that to line this up. This is probably wider than it needs to be, but we'll hang on to it for now. We'll change it if we don't like it here in a second. All right, so next let's dimension from here to here. Let's make this 1/4 of an inch because this is the main bearing. Some of the weight of the drivetrain is going to be on this bearing transferred through the shaft. There's going to be a lot of load on it. You don't want to make this wall too thin. Also, to press fits, you want to make sure it's nice and rigid so it doesn't deform when you press the bearing in. All right, then from here to here, let's make that 1/8 of an inch so that this web here is 1/4. I like the size of this. We could go down to 1/8. What the heck? In the name of being aggressive, we'll do that. Take some more weight out. Okay, so let's finish the sketch. Let's go to an extrude feature. Click on those 2 regions. Set extents to all. Now we need to go through and add fillets. We'll try to do probably 1/8 inch fillets on all this stuff as well. If there are corners, like up in this corner, you might want a bigger fillet. And if you get like really sharp corners like this, like if we place an 1/8 of an inch, it's going to fill that in. Now, in this case, I want that. Like that's what I was expecting. But if you get really, really like small angles, you place a fillet, it's going to fill that whole thing in with material to get the fillet to the right place. And so you might want to place smaller fillets in corners that are sharp. But in this case, it's fine. This lightning patterns like this are a really inexact science. Like there's just not really a lot of rules that goes into it. You kind of just want to make sure your part's strong enough, but take out as much weight as you can. All right, so this is starting to look really, really nice. So let's mirror the extrusion feature and the fillets to the other side. So let's expand our origin here. Grab our mirror tool. That's the extrusion. Those are the fillets. Click our mirror plane. Click that plane. Click OK. Alrighty, that looks pretty good. That'll be fine. All right, so now let's go to eye properties. Let's update the weight and see what it is. So that's 0.146. Now let's just really quickly let's suppress. You guys don't have to do this, but I just kind of want to show this. I'm going to suppress all of these features, kind of go back to the way it was before, and go back and update again. So 0.282. So actually we took out quite a bit of weight. So 0.282 divided by, oops, 0.282 divided by 0.146. No, I did that wrong. Okay, other way around. So we took out very nearly half the weight. So actually we took out more weight out of this than I was really expecting. But that was because, once again, we got pretty aggressive with our lightning. And then I'll unsuppress all that and bring it back. All right, this is done, so let's color this. I believe we had not figured out this whole thing. Yeah, so let's go. I need just to look. I need to remember what the colors were. Let's go to the pinwheel, Stellar Yellow, add to Inventor Material Library. I think I can just do that and just add it to the Inventor Material Library. Maybe that will work. So let's go over here. Oops, let's go to the Inventor Material Library. So just resize my window. Go to S, scroll down. Stellar Yellow, there we go. Okay. And then I can go to the pinwheel, right-click, add to favorites, and then it'll at least show up on the favorites for this part. So, all right, that should do it. Close out of that, close out of that, close out of that. Go to this. Let's open the standoff and color this. All right, does it show up in my favorites now? No. It should show up in the Inventor Material Library, though. Yeah. All right. So the standoff is yellow. The gearbox is yellow. We're not going to color shafts because they don't actually get painted. If we order that shaft material from Vex, it'll be black. If we order it from AndyMark, it'll just be the plain aluminum. I greatly prefer the aluminum stuff, or the stuff from AndyMark, just because it's tolerance better. The stuff from Vex is always tight. You have to like sand it and stuff. It's just, I hate that shaft. It's not a good product. AndyMark stuff is just really high quality. It's really good. And they're the same price. But the other problem is AndyMark is always out of stock, so we end up using Vex's stuff quite a bit just because they're the only ones that have it in stock. All right, so let's end this here. Let's look at what our weight is right now. Actually, let's update, because we need an update. When you see the little lightning bolt in here, it means you got to update. Let's go to iProperties and see what our weight is. 31 pounds-ish. That's without any electronics, of course. I think that's lighter than the kit bought, but I could be wrong. With the belly pan lightened, we can take out at least 1.5 pounds out of the belly pan, and we'll see how much weight we can get out of these. Probably, I don't know what they are weight each. Probably 1/2 pound out of each. Yeah, we can probably get 1/2 to 3/4 of a pound out of each one of these, so we can get at least 2 more pounds and 1.5 pounds out of the belly pan if we lighten the belly pan. So what does that get us? 4.5 pounds? 3.5 pounds. 3.5 pounds. So we get 3.5, 4 pounds out of this whole thing. So far, get us under 30 pounds. Be pretty good. Alrighty, thank you for watching. Tune in next time. We'll finish this up, and we'll look at what we got.